In Chapter 4, problem 17 asks us to calculate the atomic mass of magnesium. Yes, Sam, we know the answer from our periodic table, but let's see if we can actually calculate it based off their percentages. They say there's 3 isotopes with the following abundances and masses. If the mass, the isotope is 23.985, and this is in atomic mass units, the abundance of that mass is 78.99%. Second isotope, 24.986, and the abundance is 10%. And the third isotope is 25.982, and it's 11.01 in abundance. Glance at this problem without even touching a calculator. Tell me what the average atomic mass is probably going to be. This is the most abundant isotope, and it has a mass of 23.9. However, you do have a little bit heavier ones here, so we're going to say it's going to be approximately what? I agree, 24. Okay, now let's do the math. So if this is your percent abundance, and actually these type of calculations are done in when you do taxes, when you pay taxes, you have to like calculate what percent, you know, depreciation did you have between these years, blah, 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 blah. Like you end up doing things like this in real life, not just chemistry. Our school funding, when we do a student count day in September, we get like 70% of the funding then, and then we get 30% of the funding by whatever our school count or student count is in March or April, whenever that student count day is. So it's not half and half. It's not like we get it all in September. It's like this, a little bit messier. All right, so what do? We have percent abundance, so we're going to need to move some decimals. 2 places. And then we're going to multiply 23.985 times 0.7899. And then we're going to multiply, and we're going to move our decimal twice because it's a percent, so we divide by 100. If we didn't, we would end up with like thousands of AMU, and we want it to be about 24, not 24,000. That's why you got to move your decimal, because it's percent. It's how many out of 100. So if it's how many out of 1, it's 0.7899 of 1. So what are our contributions? $18.95. When we multiply that, 2.498, and we need to talk about when to tell your calculator to shut up, because your calculator is giving you a lot more numbers than 0.95, right? It's probably going 0.9487669. You don't want to write all those numbers down. So what do you round to? Your math books don't treat you as intelligently as you actually are. And they tell you, round it to the hundredths or round it to the tenths. I'm going to say, look at what you were given. You were given 2 decimal places here, 3 decimal places here. So you know you can go at least 2 decimal places, because that's what you were given. That's the kind of measurements that were taken. You're going to be just as precise as the measurements you were given. So in this one, we can go a couple decimal places, and we can say it's 2.861. 2.861 AMU. Now you might say, why did this go 3? Why did this go 3? When you're multiplying, we're going to talk more about this very soon, like next week. When you're multiplying numbers together, decimals tend to move around, don't they? So we really look at how total many digits were in this number, or figures. So how many are there? There's 4. How many are here? 4. How many are here? 4. So how many do I have in this answer? 4. How many digits do I have here? 4. How many do I have here? 4. How many are going to have in this final answer? 4 would be a good guess. So it ends up being 24.31. Is that right? And that was for magnesium. So then we could always double check and say, hey, what does the periodic table say? Am I close? 0.305. So depending on the periodic table you look at, those masses might be a little different. Tom, if I dig for magnesium in Brazil, and then I dig for magnesium in the Congo, am I going to find exactly the same distribution of isotopes of magnesium? Probably not. So the signatures of what the percentages are in a different area can tell you where it was mined from. Isn't that cool? And these values actually change as we discover more and more and more about what we have on this planet. Because your periodic table is giving you the average of all the known isotopes, right? So that average can change. And it's an average, so you're going to have decimal points, right? If I talk about one single isotope, I'm having just one AMU. But here, this is an average of all the isotopes. And that's how we do that problem. So when you look back at number 15, hopefully you can do that well. In the meantime, take a look at 16 for me. Which one is probably the most abundant? 16. I should throw a picture of it up here. I probably could. Because we have, is your syllabus coming together? You have this chem book right here. And in Honors Chem A, oh, I forgot to put chapter 4 in there. I will have to do that. What page are we on? Look at that. Boom, boom. So for number 16, helium has 2 naturally occurring isotopes, helium-3 and helium-4. Atomic mass is 4. So what's probably the most abundant isotope? The one that has a mass of 4. Which is similar to what we did here when we said, hey, if percent abundance is 78, 79%, 23.95, then that's going to be the average. It's going to be closest to that. So in 15, if boron 11 with a mass of 11, if the abundance of that is 80%, what is boron's mass probably going to be? The average is going to be close to 11 because it's 80% of your abundance. Okay? I just want you guys to have a feel for isotopes and their symbols. What would be the symbol for boron 11? This is the name right here, but what's the symbol? It's a B for boron, and then I put an 11 up here for the mass, and the number is 5. Okay, so the name has the name with the mass and a dash after it. The symbol has the mass at the top of the number here.